Hello, everyone. Welcome to the SAS Explore Super Demo, the science behind the batting lab. My name is Gunje Walton. I manage a development team in the SAS Econometrics group. Today, I'll be talking about the science behind the scenes of SAS Batting Lab. This is what SAS Batting Lab looks like. It's a smart batting cage that is powered by the SAS technology and intended to help children improve their baseball and softball swing. Yes, using AI and machine learning to improve performance at batting is a very clear use case of how machine learning tools drive success for individuals. However, SAS Batting Lab also intends to provide them with the necessary tools to enhance their data literacy knowledge by cleverly embedding data within this very high interest area of sports. So the instructional strategy here is to use that situational interest that is brought on by baseball or softball in order to motivate an interest in appreciation for the value of data. As a result, these kids see a completely different side of data, the one that is not isolated in the math classroom, but rather embedded in the real world, applied to the real world to help them solve a problem that they care about. At the beginning of this project, before we created our machine coach, we needed to answer a few questions. What's a good or optimal swing? And how a machine knows what's a good swing? Can a machine separate and evaluate the different phases of a swing? How can a machine give advice to players to improve their move? The human coaches or pro players have received thousands of hours of training. As a result, they can store the sequence of right moves in their brains. Well, can the machine do similar stuff like identify and remember the right sequence of moves? To answer all these questions and have the batting lab come to life, we follow this workflow. To train our model, we first gathered and prepared data using computer vision. We used the hidden Markov model and trained it using the data that we collected. Using an A-store capability of our analytics and SAS event streaming processing, we deployed this model to the cloud. At the end, using the sensors and cameras in the cage, we captured a player's swing and streamed that data to the cloud. Then the model can be stored. The model can score the player's swing based on how much the swing deviates from the optimal swing. We then give recommendations. This is a very high-level summary of the features and aspects of the technology that made the batting lab happen. Next, I will shed a little more light on this entire process, especially from the modeling and scoring aspects. We can have a machine to do all this as long as we train it properly. To train the machine to do the coach's job, first we needed to watch and learn from the good players. For this stage, we use data that is obtained by partnering with NC State University baseball and softball teams. From their dozens of elite players, we captured hundreds of swing videos. A video of such a swing contains about 100 frames. Here, you're seeing an example of such a video. Note that this video was not used in the training data set. Then that video footage was analyzed with computer vision using the pose estimation package to identify where each player's body was positioned in space during the process of the swing. So in each frame of a swing video, the player's joints were positioned. In the picture, you can see the frame number shown at the top, and the blue dots point out the 19 joints on the player's body, like knees, elbows, shoulders. Each joint contains XY coordinates to mark their position. Frames have a natural order. They are sorted by time. Therefore, the data we obtain from these frames are naturally time series data. The data were normalized to maintain about the same height for each player. At the end, we had tens of thousands of frames or observations of 38 variables extracted from these videos. These were the data that our model was built on. We use PROC-HMM from SAS Econometrics to fit a hidden Markov model to learn from these data. In recent years, machine learning has become very popular and has made great advances. Hidden Markov models, or HMMs, are an important member of the machine learning family, and they have been widely applied in speech recognition, facial expression recognition, and gene prediction, so on. HMMs, though, have special advantages like easy interpretability and flexibility. This makes them especially suitable for the pattern recognition tasks that the batting lab requires. The HMM categorizes the player's moves by a series of groups and labels them as the swing phases or hidden states. You can consider these hidden states as the driving force of a player's moves that we observe in each frame. They are, in a way, like human coaches, how human coaches summarize baseball positions, like the stance, load, stride, attack, contact, and follow through. The hidden states are recommended by the transition. The hidden states are connected by the transition probabilities. That is to say, there is a certain probability for moving from one state to another. In each state, there is a set of parameters determining how the data are generated in this state. For example, in a Gaussian HMM, those parameters are the mean vectors and the covariance matrices. The frames you can watch from the videos are the observable variables in the model. Our goal is to find the unobservable variables or hidden states. To do this, we first train the model. This is like training the machine to do the coach's job. This is the stage where the model or the machine watches and learns from good players. The big problem is that HMM with high dimensionality has lots of local optima. So the optimizer plays an important role here. Each observation extracted from the frame contains a pair of coordinates for every joint. Therefore, 19 joints generate 38 variables to mark the position of the player's swing. In the Gaussian HMM, there is a mean vector and a covariance matrix in every hidden phase. In this model setting, we have 38 parameters for the mean vector and 741 parameters for the covariance matrix in each hidden phase. That leads to estimating thousands of parameters because there should be dozens of hidden phases. In this case, instead of the classical optimizers like active set or interior point algorithm or machine learning optimization algorithms like stochastic gradient descent, the expectation maximization or EM algorithm is chosen. This is because it is specifically suitable for models that latent variables and high dimensionality. Now we have HMM with EM algorithm. We still have two big challenges. The first is to decide how many hidden phases are in the model. The second is that the optimization result of the hidden Markov model with the EM algorithm depends heavily on the initial parameters. The solution is to search for the models with different combinations of the number of phases and random seed. Then you need to compare their information criteria to pick the model. The Bayesian information criteria, or BIC, is used to select the model because the minimal model setting is preferred. After dozens of hours of calculation on thousands of CPUs, the model with 46 hidden phases became the winner. The figure here shows the histogram of the log likelihood of all the swings in the training data. The x-axis is the log likelihood averaged by a frame for a player, and the y-axis is the percentage. The correct swings are on the right side of the plot. The incorrect ones are on the left side. The score or likelihood only represents how the player fits in the model or how the player's movement is similar to most players. Our object is to find the optimal swing, which would give us the highest likelihood or most fit to our model. However, the top scorer in the training data may not be the one we wanted. Sometimes an unfinished swing may erroneously create a high score. So we need to view those clips and identify those outliers and exclude them to reduce the unwanted high scores and the hidden phases. After deleting the outlier data, we repeat the training steps that I mentioned before until the high scores are complete swings. You can see the flow chart on the right that summarizes the whole process. The HMM can find the hidden swing phases behind each video. We are interested in how the correct swings are associated with the hidden phases. What you see here is the plots of the hidden phases of the optimal swing, the swing with the highest score. For this swing, the model found 8 phases to explain it. There are 8 phases associated with the frames of this one particular video. However, there are 46 phases summarizing all the moves in hundreds of videos in the training data. In other words, all the hundreds of thousands of frames can be explained with only 46 phases. That's the power of automated learning demonstrated by using the HMM procedure. After training the model, the resulting model specifications were saved to the cloud connected to the SAS Batting Lab. Equipped with cameras and thousands of sensors, the batter's box captures players' moves. Next, the data are streamed to the cloud using Microsoft Azure, which provides a private and secure way to upload, process, and store data. Finally, the model can score the player in real time and show the measurements and feedback on the screen of the SAS Batting Lab. So the players can get information back immediately and work to improve their moves in the next round. Here, a young player's score is located to the left of the college players' scores. The mean log likelihood of the college players in the training data set is 119. The young player's score is 60, implying that there is a definite room for improvement. To give concrete advice on improving the swing, we scored each frame based on the model that we trained. A frame scores low if it deviates a lot from the swing phase that HMM recommends. For example, here, frame number 102 has the lowest score. For this frame, the hidden phase recommended by the HMM is shown in the plot, and the corresponding move is on the right. You can tell that the shoulders are not even, the hands are in different positions, the distribution of the weight is different. We used some rules to automatically give advice based on the differences between the move we observed in the frame and the recommended hidden state. And after the player improves their ending move, we can score their new swing again and find another deviating frame and give new recommendations. These pictures are shown to the young players on the screen in the batting lab. As I mentioned, the frames are used to identify the phase of the swing with the biggest issues or deviations, and then that is combined with the business rules by professional coaches creating feedback for the players. For the feedback, we work with the coaching staff of the NC State baseball and softball programs and kind of identify the areas of the swing, prioritization type of improvements that can happen in each phase, and then map that to specific language that is age appropriate for these players to receive. Overall, this project involved many products. The data from the video footage was analyzed with the computer vision using the pose estimation package. For the hidden Markov model, we used PROC-HMM, a procedure in SAS econometrics on VIA 4. For the whole scoring system, we used cloud technologies in Azure and SAS events streaming processing. Right now, from the time that a player swings the bat, and we get that video back, to the time we can recommend improvements to their swings is about 5 to 6 seconds. With this demo, I tried to give you an overall view of all the pieces that made up this project, with the emphasis on how the underlying model was built and implemented. I recommend you also watching the breakout session for the Batting Lab, where you can see the big picture in a more detailed way. You can also find the other two analytics sessions very useful. The second one informs you about the newest techniques available in SAS Voya for everything related to your data. The last one is about how you can use Model Studio for building your models, which is a critical phase of the analytics lifecycle for machine learning, text analytics, and forecasting. You can always reach me at this email, and thanks for watching.